Aluminium component, you can use the exact same design for magnesium. So that's something you should know. In terms of damping properties, so magnesium has excellent damping coefficient. So it is crack resistant, impact resistant metal, and it has 20 times better shock resistance than aluminium. So at the least, and there are alloys which have significantly higher as well. In terms of shielding, they have excellent properties. EMI, EMC shielding, great properties there. Good thermal conductivity. Right now, we are seeing handheld, mobile, wearable, EV, anything that moves or is expected to be mobile or carried by the user is now transitioning very easily to magnesium. So you should seriously consider, if you've not yet considered for your use cases, you should consider this material. AZ91, I think I'll just cover the two alloys. So aluminium, A stands for aluminium, as you can see the table on the right. So aluminium is for A and Z is for zinc. So this is the aluminium zinc alloy, which is the second, the other two high alloy contents. So aluminium is 9%, zinc is 1%. That's how you understand alloys in magnesium. So aluminium zinc 9-1. And another famous die casting alloy that is used in India is aluminium manganese. So aluminium manganese 5 and 1, 5 and 6 and 1, those time. In terms of aluminium, I don't think anybody needs any to be told what aluminium is. LM24 and ADC12 commonly used in India. High ductility, lightweight metals produced abundantly in India. Usually used as a replacement for steel in wherever lightweighting is involved. And use cases are more than obviously what I've mentioned here. So, but these are the two commonly used alloys. A little deeper in terms of comparison, here, as you can see, aluminium does great when it comes to thermal conductivity and in terms of cost per unit. Magnesium does well when it comes to damping coefficient, the weight, density, amount of draft, castability in thin walls, shielding, machinability, recyclability, die life, cycle time. These are things that magnesium does better. Just to give you an understanding of what price point you should expect. So for the net finished component, you can, so this is the raw material price. So 325 per kilo is what magnesium is currently at. 200, around 250 is what aluminium would be at. This obviously changes every week. So this is an older presentation. I've mentioned what, but this is mostly it would be close to reality. The casting rates, if you see, it's 550 to 1000 per kilo, ranging depending on the part and the machine. And here also you would see that 350 to 550 is the part price. So per kg, so you can understand. And this is also an old presentation. I've not updated this, but you should expect 200 to 500 for zinc. Way of understanding how the densities would play a difference is if you're making 3 components out of 1 kg of magnesium, you're making just 2 components out of 1 kg of aluminium and 0.8 out of 1 kg of zinc. So that's just a understanding of how savings could be done when just with the density difference. The other aspect you should know is that like I mentioned, 1 lakh shots is something that is the average industry expectation, but magnesium has a significantly lower affinity to steel, and therefore their dies last longer. So 1 lakh shots for if you're spending 10 lakh for every die, every 1 lakh shots, 1 lakh units, you would spend that same 10 lakh rupees will get you about 3 lakh components or 2 lakh components at the least. So it would last longer, and that's where another aspect of the saving would come in. In most, some features of the part, you would sometimes not require load-bearing strength. You just need stiffness. So in these kind of features, you can also reduce wall thicknesses, and you'd get. This is just a comparison of wall thickness, how much basically stiffness at equal weight, weight at equal stiffness. So if it's 1, magnesium is 1, aluminium is 1.8, and steel is 2.1. This is just an example. The last section is about some of the insights. Now, if you're considering to start doing high pressure die casting, the first thing you would, what I would recommend is try and consider a single cavity prototyping tool, H13 hard tool. try and use a smaller machine. That's what will get you started. If you think that the cost is too high for your initial prototyping and testing, then the ideal other way to do it is a P20 tooling die. So this is a softer tool steel. It will last you only 500 to 1000 shots. This is not something that everybody knows or does, but P20 tooling is something that you can consider. It'll reduce the cost for tooling for you initially. The next is about 3D printing of prototypes. Some customers request that they want a prototype in die casting to check fitment and do their testing. You can also 3D print it using polymer or metal, just to, if you want to do fitment with drafts and with all the new design considerations that you've done. You can also prototype using sand casting and machining it with the allowances and all the design considerations to do your testing and fitment. One thing to keep in mind is if you take a forged block and machine that out into that component, into that prototype, forged material is closer to die casting properties, slightly higher than die casting properties, but still closer to die casting properties. Whereas sand castings are significantly lower. So there are two ways you can go about it. So you can either do a sand cast prototype and do your mechanical testing or physical testing. If it fails, then there's a challenge. But say if it passes even in sand casting, you have significant confidence that you in a die casting it will easily pass, right? It will easily manage the loads that are involved. Whereas forging is for a if you want an alternative, the only other is slightly higher than die casting, which is forged material. So I've seen customers go with both. Sometimes they go with forged material, sometimes they go with sand casted material, whatever they require to get their approvals in that sense. The last one is probably the most valuable. So you've tried earlier, I mentioned single cavity, too expensive. P20 tooling also, you think it's too expensive. The last version that I can offer is basically there are products, dies that a die caster would have, which are where the products are decommissioned, right? The products are out of production, so those dies are there, but those products no longer are made. So the housing of those products are still lying around. They're fairly good housings. You can just replace the insert in between. Just make an insert out of P20 or S13. So I'll just take you back to that first image so that you understand. So here you see this is the insert. So the housing, as you see, is majority of the metal. The insert is a small thing, but the insert costs the most amount of money because it's H13 and there's a high level of precision machining that is done. So the insert is what is expensive. But at least you can do significant weight saving, like cost saving, by making the house using an existing housing that a die caster might have. So that is the last way that I know that you could possibly reduce the cost of getting into die casting. We do this depends also on the kind of housings that we have and whether it would suit your part or not. The size would suit your part or not, and all of that discussions have to be had. But this is something that most die casters should also have. Just a couple of slides about us. We are at our core, we think of ourselves as a material science company. We are just trying to help innovators build the next generation of energy efficient machines, and we are doing that using lightweight material. So we believe that magnesium is that material that can help innovators unlock a different level of performance that is required for the future of machines. So that's how we think of ourselves. And uh, I've covered processes earlier. So we are not just a high pressure die casting vendor. We do any component you give me, I'll be able to manufacture. Either we have that in house or we have partnerships with vendors whom we've developed over the period of our 28 years who can help us with the external processes. Just a few components in high pressure die casting that we've previously done. These are optoelectronic components. As you can see, quite a lot of features in this in all directions. So a few components in consumer electronics. So this is the middle one is a compass, a mobile phone, a smart lock, again battery housings. These are slightly larger, some of the larger ones. So this is a seat frame for a metro. This is a radar that goes on our border. So this was made of both in LM24 and also in magnesium. A size of 500 by 500. This is a 2.5 kilo casting. This is for aviation. We've done a few components for automotive, steering wheels, pillion rider handles. Actually, these are just some of the hundreds that we would have done. So here's a few more just examples. Here. All right. So you now know the design considerations to keep in mind to design it. But if you do need us, we all also help with the design aspect. So if you have your existing component is in steel or any other material and you want to transition to magnesium or aluminum, we can help you redesign that component for that new material, for the new die castable material, right? If you need any kind of design optimization support, we can help you with that. We also design right from scratch for some of our customers. So that's something we have in-house capability of. And analysis. So any kind of FE analysis that you might need, load testing or anything else for your component, we can do that. We work with some of the biggest names